Okay, so now we're going to take a look at single replacement reactions. Single replacement reactions are where I have some type of, and so let's draw a pictorial representation of this. So let's say that I happen to have some solid, like this right here is solid potassium. Why is it solid, by the way? Because that's what it comes as when it's in its elemental state. So it's in its elemental state, I have potassium. It turns out potassium is pretty reactive for a metal because it's in group 1. It totally wants to get rid of its electron as quickly as possible. So if I am to react, if I take potassium and I drop it into a bucket containing, I don't know, let's say some salt. And the salt that I have in this container is, sure, magnesium 2 plus and Cl minus. So Cl minus. So I have a bunch of ions. This is an aqueous solution of magnesium chloride. Okay, so I have an aqueous solution of magnesium chloride. Okay, so potassium is dropped inside of magnesium, a magnesium chloride solution. This right here is aqueous. This also could be a liquid if we're talking about water, but generally we have an element and we have some aqueous solution. So if I take this and I just drop it into the little bucket there, what do we end up with on the other side? So now I've got this little bucket that, or my little container that now has a bunch of magnesium or potassium in it, as well as my magnesium 2 plus and my Cl minus. Well, it turns out the most reactive is going to want to be in solution. The most reactive is going to want to react. So the most reactive is not stable. It does not want to be its element. So the most reactive will react and become aqueous. Okay, so becoming aqueous means that it has become an ion and it's happier as an ion than it is as the element. So in this case, potassium is more reactive than magnesium. And so we end up with magnesium switching spots. Magnesium is solid. Why is magnesium a solid? Because that's what it looks like when it's an element. Magnesium as a solid and potassium chloride aqueous as the aqueous solution. Okay. We're going to quickly balance it. 1 potassium on this side, 1 potassium on this side, 1 magnesium, 1 magnesium, 2 chlorides, 1 chloride. So I'll put a 2 in front here, and let's start again. 1 potassium, 2 potassiums, put a 2 in front, 2 potassiums on both sides, 1 magnesium on both sides, 2 chlorides on both sides. It's balanced. That's all we have to do. The reason that I know potassium is going to be aqueous, again, is because it is more reactive. Out of the 2 that I have, I'm always going to replace either the cation or an anion. I know that of these 2, that is more reactive. I'm never going to ask you, I'm just going to ask you to be able to recreate the reaction. Okay, so I'm going to go over this. This is how we base it. This is the activity series: more reactive, less reactive. Or if we're dealing with nonmetals, more reactive, less reactive. Okay, so if I were to mix, and I'll use the nonmetal one now. If I were to mix, let's say, chlorine gas with potassium iodide, aqueous. Okay, so we always start with the element. That's the element. Chlorine comes as a diatom. It comes as a gas. That's what chlorine looks like when it's an element. Chlorine likes to form negatively charged, likes to form anions. So we are going to replace iodine with chlorine on the other side. So what that means is iodine is now also likes to be actually, it likes to be a solid, but it likes to form the diatom. Iodine solid plus potassium chloride as aqueous. Okay, so iodine, these two have essentially switched spots. That's what we're trying to do. Finding out which one the element belongs with is able to switch with. So if the element forms an anion, it's going to switch with the anion. If the element forms a cation, it's going to switch. All right. If this is a better way to think about it, if this is a nonmetal, it's going to switch with the nonmetal. If this is a metal, it's going to switch. So if the element is a metal, it's going to switch with the metal. If the element is a nonmetal, it's going to switch with the nonmetal. That's a much simpler way of looking at it. Again, element, aqueous, element, aqueous. I'm not going to hold you over the coals if you don't know that iodine comes as I solid. Okay. All right. So that's it. That's how we kind of identify these things. I'm going to write a handful out, and I'm just going to have you write out what it should look like. Okay. Again, when we're doing this, we are kind of doing the same thing over here on this side. I've got iodine, which I know forms I minus, but it's going to become an element. So we're just going to create an element out of it. I know I'm going to be combining potassium with the element on the other side, and that's how I got KCl. So much like we were doing it above, where I'm switching partners. If it's alone, I'm just creating an element out of it. If it's together, I'm creating an aqueous compound out of it. Okay. Okay, and I'm going to come back to this activity series. We're not going to worry about it now if you want just a little bit of extra information. So I'm going to pause this for just a second while I come up with some examples, and you should try them as soon as they pop up. Okay, so here we go. I didn't add phases because it's worth kind of looking at for all of these. And so let's kind of go through and let's do the phases first. So let's just take a look at these one at a time, and we don't need a whole lot of space to do these. All right. Hydrogen, H2. I know hydrogen comes as H2, and hydrogen is in fact a gas. We can look back at our solubility tables for these compounds. What do I know about silver nitrate? Again, what I know about nitrates is they're always aqueous. Okay, so silver nitrates are always aqueous. So H2, and so that's step one, is to make sure we have the phases sorted. You pretty much always get the phases, but it's worth looking at. Hydrogen likes to form H plus. Okay, we know that it likes to form H plus. That means that hydrogen is the one exception. Hydrogen is going to interact with silver, and in this case, silver right now is Ag plus, and nitrate is NO3 minus. Okay. Okay. Hydrogen is in fact more reactive. So we are going to have silver on its own, plus I am going to have hydrogen combine with nitrate, okay, which one of each makes it balanced, so HNO3. And what I know about nitrates is they're always aqueous. What do I know about silver in its elemental state? It should be a solid. And that's it. We are done. That's all you needed to do. Hydrogen and silver are going to switch spots. And so we've got silver solid, we've got silver elemental, and nitrate, HNO3, as an aqueous species. Okay, good. So that's it. That's the problem solved. We have done it. This would happen actually. So you can displace silver with hydrogen gas. And you saw this in lab when you added copper and silver nitrate together. You ended up seeing that silver on the bottom. All right, next up, magnesium. Magnesium forms a solid, and HCl, which is going to be aqueous. Back to the first one. I've got two hydrogens. I've got one hydrogen, so I'm going to add a 2 in front of here. Two hydrogens, one nitrate, two nitrates. So I'm going to put a 2 in front of here, and then a 2 in front of there to balance that out. So that's what you should end up with. Hydrogen, 2 silver nitrate, plus 2 silver, plus 2 HNO3 was nitric acid. Okay, next up, magnesium. Okay, magnesium likes to form Mg2 plus, and we have H plus and Cl minus. Again, all I'm doing is this to say these two are going to replace the metals, and the hydrogen are going to replace each other because they both like to form positives, meaning I'm going to switch their spots. So magnesium is going to be, oh, I'm going to start with hydrogen. So hydrogen is going to be on its own, and magnesium 2+ is going to combine together with the chloride. So hydrogen as an element, magnesium likes to form magnesium chloride. Hydrogen as an element likes to form H2. Magnesium likes to form, and we know that that's a gas. And magnesium chloride, if you look at the solubility table, is aqueous. That one is done as well. Problem solves. Okay. Next up, again, I want to point out element, aqueous, aqueous. Oh, I guess the last part, let's balance it. 1 magnesium, 1 magnesium. 1 hydrogen, 2 hydrogens. I'm going to toss a 2 in front. Start again. 1 magnesium, 1 magnesium, 2 hydrogens, 2 hydrogens, 2 chlorides. 2 chlorides. It is balanced. We're good to go. Next up, lithium. Lithium, like all metals, likes to form a solid. Iron sulfate is aqueous. We can look at our solubility table and find that out. Again, in this case, lithium is in group 1. It likes to form +1. Iron is a metal. It is going to form +2 here because I know that the whole thing is neutral. There's 1 iron. Sulfate forms 2-. So that means that the iron being 2+ and the lithium with the sulfate. The iron is going to be by itself, so I'm just going to make it neutral, make it elemental, and we know that iron is going to be solid. Plus, I need 2 lithiums for that 1 sulfate, and we know that anything in group 1 is going to be aqueous. Let's balance it out. 1 lithium, 2 lithiums. I'm going to toss a 2 in front. Start again. 2 lithiums, 2 lithiums, 1 iron, 1 iron, 1 sulfate, 1 sulfate. Done. That problem is solved. Last one, F. F-, lead and oxygen. I know oxygen is 2-, and there are 2 of them. So the total is -4. That means lead has to be +4. Lead +4. Okay. That means the negative and the negative are going to switch spots. So oxygen is going to be on its own, and lead 4+ is going to combine with the fluorine- to make the compound. So oxygen likes to form oxygen gas. Lead plus the 4 fluorines to give me a neutral compound. Fluorine, by the way, is a gas. It is the most reactive element. It catches everything on fire. And we're just going to call, we don't have any oxides, so lead oxide, we're just going to call an aqueous because it doesn't really matter. All right, so that's it. Last thing is let's balance it. 2 fluorines, 4 fluorines, so I'm going to toss a 2 in front. 4 fluorine, 4 fluorine, 1 lead, 1 lead, 2 oxygens, 2 oxygens. Everything is balanced. We are good to go. So that's pretty much it. That's how we solve these single replacement reactions. The last little bit on all of this, again, you don't need to know this, but I'm just going to go through this list and I'm going to kind of look, I'm going to highlight some, I'm going to point some things out to you. So what I want to point out is the fact that let's just look through this list, and I'm going to highlight. I'm going to use so I'm going to use orange here. Orange here is going to be group 1. Okay, so I'm just going to highlight group 1. So let's see, lithium, sodium. Okay, what else? Lithium, sodium, potassium, rubidium, and cesium. We have cesium on here. We do not. That's fine. Sometimes you don't. So that was group 1. I'm going to use, I don't know, green for group 2. So there's my green, or blue for group 2. Okay, so group 2. Oh. Group 2. That's a terrible G. Group 2, we're going to use the blue. Okay, so beryllium, there's beryllium, magnesium. Okay, beryllium, magnesium, calcium, strontium, barium, strontium, calcium. Okay, do we see a trend between group 1 and group 2? Yeah, we absolutely do. The trend that we see is group 1 is more reactive than group 2, except for sodium. Okay, so the reactivity is going to follow the periodic table a little bit. And let's take a look at, this is going to be other metals. So these are, what I'll just call these actually are D block or G block plus. So other things that are in the D block. So aluminum, manganese, zinc, cadmium, iron, cobalt, nickel, tin, lead. Yeah, so all of those are in the D block. They're all below group 1 and group 2, so they're a little less reactive. Let's use the yellow one are going to be these coinage metals, right? Remember the coinage were the precious metals. If you look, copper, silver, and gold, platinum. By the way, copper, silver, gold. We've got platinum, and I've got mercury. Notice that they're all kind of right here in this little upside down T on the periodic table, 29, 47, 79, like all of those are the atomic numbers. So what we're going to notice is copper, mercury, silver, platinum, gold, and palladium. And palladium is actually right there as well. So I guess I could add that, palladium. So they're all in that one little location. They're the least reactive. Hydrogen is less reactive than metals, but more reactive than the coinage metals. So point being is there is some rhyme or reason to the reactivity table. Okay, and we're not really going to worry about the non-metals. We really look at others mostly. But you don't even have to know that. I'm just kind of letting you know just for a little information if you want. All right, good. So that hopefully should give you some practice doing these things.